So today I'm going to be talking about some projects that are largely about securing what we call the convergence across domains, mostly in industrial control systems. So we'll show some examples, but it's mostly critical infrastructure that keeps our society moving, right? Also, sorry for whatever reason, my clicker on my laptop is a little jumpy today, so some of the animations may be a little bit buggy. But when we talk about across domains, it's not only about modeling, how traditional cybersecurity vulnerabilities impact the physical operation of our society, but also common vulnerabilities that we see across physical domains. So common attacks in, water treatment and oil treatment and power grid, things like that. So, so we're going to talk about a few of those projects, but to kind of introduce myself a little bit, so my research is mostly in industrial control system and IoT security, safety, and privacy. So some things that won't be today on today's slide deck are some of the more safety and privacy aspects, as well as some of the work that we're doing in explainable AI for sensor data and other medical IoT projects. And so I just started this IO Trust lab at University of Utah, and we just have our website's under construction because we just started last month, and we have 5 PhD students and 4 undergrads. We got them all at once, so it's been a bit. But the website is coming soon. And so to kind of give an outline for today, or roadmap, right? We'll first talk about what we refer to as the security of engineered systems, or cyber physical system security, right? These are existing engineered systems that we often have to retrofit security on. And we'll talk about what we mean by that. And then we'll talk about what are cross-domain threats, and then show why we need to sometimes retrofit security. So that will lead us into our next stop. So if you can't patch an existing system, how do you figure out ways around it using the physical dynamics of the system? And then our last stop before we conclude will be about some of the research infrastructure projects that we're building and ways that you can also engage with some of this research in the coming year. So we have a little Bronco that will guide us along, and so we'll motivate the problem a little bit in this first stop. So again, sorry for the jumpy transitions. So a lot of what we work on is these are 4 of the critical infrastructure identified by SICE, where some of them might be electric power grid, nuclear reactors, factory automation, or that we see that, or even water treatment. And water treatment itself is a pretty diverse field. It could be wastewater treatment or drinking water treatment, things like that. And they're increasingly under attack in recent days. We see all these headlines coming out. Stuxnet might be one that you're familiar with. There's a bunch of power grid attacks in steel mills, and you may have seen this. Oh my gosh, these animations are killing me today. But in general, the main objective of these attackers is to maximize physical impact through stealthiness, right? Sometimes they just want to take these systems offline, but their goal is to really, make a more enduring effect. And we will see that. I'll go through, for example, the Stuxnet attack and what they did. And so to kind of give a primer on industrial control systems, and the backbone of a lot of these systems are the same. Usually, they may have some, different infrastructure, but for the most part, at the top, you'll have a management level, and this is usually supervisory control and data acquisition. These are folks monitoring the overall operation of the system. And these are interacting with the control level devices. And so these are usually, the internal networked devices. You have an HMI, which is a human machine interface. You can think of these as the panels that you'll see in an operator floor. And then the other components, or the critical components that are usually targeted in these attacks, are these programmable logic controllers, which I describe sometimes as a cyber physical interface, where this is a point where the control commands are actually translating to some analog signals that are controlling the field level devices. And these are all the actuators of your system. And this is where the diversity comes in, right? Could be a water treatment plant, could be power grid, whatever it might be, right? And so one of the representative attacks in this space was Stuxnet. Is anyone familiar with Stuxnet? Okay, yes, I see some nodding heads. So this is an oversimplification of Stuxnet and really the end, I guess the payload, right, of what Stuxnet was trying to do. And so on the left, we have the programmer operator that's, that's programming these PLCs. And on the right, we have the system that's actually interacting with the physical system. And there's this Step 7 software that's used, the Siemens Step 7 software that uses this DLL library that facilitates communication. So this is on a Windows PC and it's facilitating communication from the programming IDE to the PLC, right? And so the way that Stuxnet worked was that it renamed this DLL and it essentially intercepted communication between the programming DLL and this programming environment so that it would allow them to intercept any communication with the programmer. And not only on the programming side, so it could upload any code, malicious code to the PLC, but then it could also report false measurements back. So that on the left, program operator might say it looks good, but on the right, things are going chaotic, right? So in this case, they're attacking centrifuges in a nuclear reactor in Iran. So again, this was an oversimplification of the Stuxnet attack. And a more advanced attack that we worked on, again, these are just kind of giving you an idea about what types of attacks are being not only in the real world, but also in research. So this was actually our attack that we did in NDSS in 2017, where we developed this model-aware rootkit, and essentially, made malware aware of the physics of the system. And so the idea is that it would take into account the topology of the industrial control system, meaning try to understand what it's connected to, and it used a physical model to drive some adversarial objective function, right? So this could be, whether it's a water plant or power grid, right? We want to make it aware of the physics and understand what are the sensor values, and then try to mount some objective function, right? And so in the paper, we described how we actually infected the firmware. There's a number of ways you can do it. But the key point that I want to talk about in this attack was we were able, so this is kind of a simplification of this previous diagram that I showed with the overall operation of the system, where at the top you have an operator with some legitimate control logic, and there's some firmware in between, and then you have the physical system at the bottom. And the way that this worked was we would essentially, in the firmware, split the firmware into two models, where at the top, we'd have a benign model that was taking legitimate control measurements and then calculating what the fake legitimate looking measurements would look like. And then at the bottom, we would have some malicious model that was driving some adversarial malicious control. And this gives you, rather than just recording and replaying those sensor measurements, it gives you a more dynamic attack that you can mount on these systems, and it gives you more flexibility. So this was just one physics-aware attack that we worked on. And wow, these animations are going crazy. So we evaluated this on a power test bed that was at Florida International University that had all these different components. And we had to, we hacked into a PLC, and to implement the firmware rootkit, we took it apart and we did some reverse engineering to figure out how the firmware was, composed on a real system. And we use this to develop our payload. In the paper, we talk all about this. But the end result was that we were able to, essentially on the left, this is what the human machine interface of the operator was seeing. There were some minor perturbations at the beginning, but the actual system measurements of what we were attacking, it drove the power system to some unstable limits. So it's just one example of, kind of a more advanced attack and there's been a lot of research that's stemming from this now. And in general, right, the trouble with these SCADA or these ICS systems, so SCADA stands for supervisory control and data acquisition. Oftentimes they're designed, these systems are integrated to so many aspects of our society, and they were designed, 20 years ago and thinking that they'd be isolated with no security in mind. And for the most part, that access was local, not remote. But today, everyone likes convenience. So, everyone likes AI, everyone likes, being able to remotely operate things. So when I interned at Siemens, for example, who was the primary target of the Stuxnet, they're developing a lot of, PLCs that you can access with your Android phone, things like that. And nowadays they're talking with COVID, they're talking about distributed control systems where, operators can sit anywhere in the world and, control their system, right? Going in the wrong direction. So it's just a challenge, right? And there's a lot of issues where there's vulnerable proprietary protocols that are baked into the hardware, and they're extremely hard to patch. And also there's a lot of pushback from the vendors and the operators to want to take their systems offline. For the most part, we talk to municipalities and they're saying, you as a systems integrator, you would push them to buy all this infrastructure that's cost millions of dollars on a limited government budget. And then now you're asking them, okay, now we need to replace that hardware with, another $1 million equipment. They're very reluctant to do that. And why would they trust that the next set is going to be, trustworthy, right? So, and one key, right? So this was from a report from CISA, this ICS advisory report, and they describe what are forever day vulnerabilities. These are essentially vulnerabilities that are architectural in nature, and there's not a really simple way to patch it remotely. It's not a software bug. It's just baked into the hardware. And so usually organizations will have to deal with these for a very long time. And they found that, there was in their advisory report, and this was just for one half, they found there were 227 new vulnerabilities that were in prominent vendors that had these forever day vulnerabilities. Right. And so in general, we have these systems where again, this is another simplified overview of an industrial control system. And you have what we call this control systems engineering workflow. And this starts from some physical modeling. And then there might be some modeling and simulation. So you can think of MATLAB or Simulink or whatever you're using to model your, this physical model, right? And then from there, there might be some generated controller code that goes onto these systems, and that gets put into your system, right? And so traditional cybersecurity focuses on, the software and network vulnerabilities that you see here. But what we're increasingly seeing is that attackers are focusing on what we call the operational technology, the physical side of things, right? And there's unique attacks that we've seen. We've shown a couple examples, right? And so what a lot of my research in this space does is trying to leverage the physical semantics, so the understanding of what's happening in the physical system, to what we call retrofit security on these legacy systems, right? We can't just simply patch them. We have to figure out ways to look at the sensor readings and think about, okay, can we detect discrepancies in the overall operation of the system? And this is when I just want to point out that now there's, everyone likes to, create buzzwords and phrases. So when I was doing my Ph.D., we call this cyber physical security or cyber physical system security. And now people are referring to this as the security of engineered systems, because there are oftentimes, there's a lot of engineering that went into these systems, and we kind of have to treat them as they are and then figure out a way to retrofit security onto this engineered system without, ruining the overall operation, right? So I know I'm going kind of fast, but any questions yet?
I have a question.
Sure.
When you're talking about the objective attack functions, are those predefined or is it creating that on the fly?
So that's a great question. So in different, so discovering those physical dynamics, in our paper, we mentioned that there is a lot of state estimation software that exists. So when you're, for example, in the power grid, you have state estimation software to figure out, okay, what will happen if I, change the operation here, and you try to simulate what that is, right? And I was just talking with a systems integrator at that builds a lot of these systems in Los Angeles. And what he said is, I asked him how he would attack a system, and he goes, the first thing I would do is compromise the SCADA system to figure out what's the operation and figure out what's the, how these things, what's the physical topology, what are the dynamics, things like that. And then I'll mount my attack accordingly. Usually because the SCADA systems are connected to the internet, so they're easier to compromise than the ones that require more advanced attack at the operational side. So yeah, did that answer your question?
Yep.
So you're like, suppose we have the X1, X and X2 parameters, so you're generating values for them, right?
Yeah, so it depends on the attack, right? So we're going to go through, yeah.
But then do you use a kind of SMT solver or just adversarial networks? So
in this talk, I don't talk, so there are ways to model the sensor values and model, so I have one slide at the end, I think, that where we talk about how we model from a more formal methods perspective. How do we verify the safety of the system? And yeah, there's certain types of logic that we use. So SMT is sometimes used as to find counterexamples, but we try to, in that project in particular, we use deductive verification logic. But in general, yeah, I don't want to get too far ahead, but I'd be happy to talk about that more offline. Yeah. Okay. So talked about kind of the broad space, right? And now I want to talk about some of these more cross-domain threats and kind of formalize some aspects of this research. And so in general, right, and this is actually what a slide from my cyber physical systems security course. When we're talking about cross-domain threats, so traditionally we think about them as, cyber versus physical, or information technology, IT versus operational technology, convergence. And when we think about this, it's usually just any security or privacy failures that lead to some physical threat. And in this case, this is an example of a smart home where, someone breaking in or hacking into a system may lead to some physical harm or financial harm, or maybe some other aspect where, you're trying to mount some physical attack on the system, right? But then, so that was traditionally when it started out, people were trying to just have a simpler formalization of these cross-domain threats. And then DARPA came out with this program recently that was called DARPA Fire, where they were trying to figure out, okay, what's the difference between a cyber and a cyber physical threat, and whether there is a difference, right? And they had their own way of thinking about this, where they said, maybe these are vulnerabilities that arise from the composition of these systems. So it's not necessarily that each individual component may have some traditional software vulnerability, but the idea is that if they're composed in a particular way. So for example, this was a drone example that we're using where you have some sensors that are mounted on a drone. The drone code is fine. And then if this particular drone is in flight and then a speaker is, injected into this and causes vibrations on an accelerometer, for example, and then that leads to some errant readings in the sensor values, then it would cause a crash. And so here they're talking about how, maybe the components individually aren't vulnerable, but this is what they discuss as a cyber physical threat. And so this is just kind of formalizing, what we mean by cyber physical threats. In our case, we try to think about, the previous slide where, you could actually we kind of encompass both, right? So we think about not only how we can you know like how the vulnerabilities will lead to some physical threat, but also you know can you leverage some of the physical dynamics as well. And then we also see that in this same advisory report that I talked about, right? There's a lot of you know different physical domains that are attacked. So in these vulnerabilities, most of them were in critical manufacturing and in energy. And so these are all the vulnerabilities just for the first half of 1 year across all these diverse physical domains. And then within each of these, right, you have a lot of diversity within each critical domain. And there's a lot of common vulnerabilities and a lot of common vendors that are used, a lot of common vendor products. So while they're diverse, they add a lot of diversity in terms of how we model the physical semantics, but not necessarily, you know, kind of these common components, right? And again, this is just more stats, I guess, of what we see across different domains and how, again, even though there's a lot of different types of physical domains, right? There's a lot of common products that we see, Siemens, Rockwell Automation, Independent, things like that, right? And so in general, you know, there have been attempts. So MITRE provided, is anyone familiar with the MITRE attack framework? I see some nods, right? And so we try to figure out, okay, you know, if we have all this diversity, right, we start to find some common patterns in what attackers are trying to do. And so MITRE provided, they traditionally provided this attack framework to model the tactics, techniques, and procedures that you see in the wild. But then they created this specific industrial control system matrix that was trying to model these types of threats, right? And they talk about, okay, initial access, execution, persistence, evasion. So we've kind of hinted at some of these where you talk about, you know, maximizing the physical impact while maintaining stealthiness and doing the discovery of what the physical semantics are. And some of the research that we've been looking into more recently has been about what about how the diversity in the physical semantics, right? So this particular impact at the end talks at a high level, well, loss of safety, whatever it might be, right? But what we're trying to do more recently is thinking about what are the commonalities, you know, across these physical attacks. So as an example, you know, this is a paper that we're presenting, I think, next Monday. You know, if we have, one particular industrial control system, in this case, water treatment. This is actually a very small part of a water treatment plant. It's like it covers like 2 out of 6 processes. And they have all these components that we've hinted at. And we, from the literature and from, a lot of these test beds that we've seen, there's a lot of common ways to attack these systems. It might be, attacking pumps. It might be causing overflow in the tanks, poisoning the water, things like that. And then we may have another test bed that we want to model, or another industrial control system. So in this case, this was actually modeled after a test bed that we have in our lab that uses, instead of chemicals, it uses food coloring to dose some water, and it's running on Raspberry Pis. And we may come up with some other threats in this space. And what we're trying to see if we can figure out, okay, well, I see that some of these, there's some common abstractions here, and then I may have an additional, industrial control system, such as oil treatment in this case. And here, there's a lot of, common abstractions, such as valves, pumps, things like that, right? And I see that they're, in the water domain, there's all these different types of attacks that target the valves, the physical dynamics. So can we infer, a similar set of abstractions that, maybe they'll want to overflow some components, maybe poison the treatment process, things like that, right? And so this is an ongoing work that we have, where the goal is to really figure out ways to abstract this to common knowledge base across all these attacks that we see in the wild, and see if we could represent this using, in this case, knowledge graphs, and see if we can map these common abstractions across these systems so that if we have a huge knowledge base of different, with varied information of different industrial control system attacks, can we then infer that, okay, I have an oil treatment, what are the attackers going to target? And so this is, one particular space that we're looking at, right? In terms of how we model these cross-domain threats. And so we mostly talked at this point, let me just share I'm on time. We mostly talked about, the threat space, but now we're going to talk about, okay, well, we have all these cross-domain threats. They aren't patchable. They're forever day vulnerabilities. So how do we retrofit security solutions? And so I included two, for the sake of time, I included two of, a few projects we have in this space. But I'd be happy to chat more about things we're thinking about. So we have two projects that I wanted to discuss that leverage, this was what we call physics for the sake of security, where, for example, in the first problem, we were talking about how some of these legacy devices, they can't be patched or can't support some trusted computing base for testing that, they're going to be securely operating and we can't provide these patches. So we had one paper where we were looking at what we call physics-based attestation. And in this case, right, it's augmenting the idea of remotely attesting or verifying, the software that's running on these systems, but also including the physical dynamics as well. And so what it looks like is really using encoding the software measurement into some attestation report. So the idea is that we can, measure, from a security perspective, right? Measure what the software is currently on the PLC, and then encode it into the physical dynamics. And in the paper, we talk about how, for example, if you have a robot arm and you can encode the actual software measurements into the movement of the robotic arm. And this allows you to essentially challenge, the robot itself and say, like, we're challenging you to test the software that's running on and the control logic associated with it. And then we look at the sensor readings and we look at the report. And so the idea is that the software measurements are encoded into the physical dynamics, and it allows us to detect these types of attacks without additional trusted hardware. So the takeaway is that we use the physical sensor measurements that at the intersection of the code measurements to attest the software and make sure that there aren't any discrepancies, right? We're challenging the physical control of the system. So that was one in a nutshell approach of what we did. And then we had another paper where we wanted to take a more traditional software control flow analysis technique to monitor essentially monitor the control across different PLC devices in a control system. So this was what we called control behavior integrity. And the idea, it's similar, right, where we wanted to use, this was called SCADMAN, and we provided this control behavior intrusion detection in a distributed setting where we provided this hybrid digital twin model. Again, the idea was to have a monitor of the software running on these systems, and then also have a state estimator where that state estimator could be, aligned with the existing state estimators in the system, right? We talked about the power grid setup and all that, power grid state estimators, things like that. So if we simplify, again, water treatment example, and we have some tank that's being treated with some chemical dosing process, and you have some controller that's monitoring the sensor values in the system and then maybe controlling the valve. So we may have some oversimplified code that says, if S input is greater than 0, open this valve, else close the valve, right? So very simple code structure. If we're looking at this from a program analysis perspective, this will break down into some basic blocks where you have a branching condition on this. Well, it says Y input, that's a typo, it should be S input. And so if this input is greater than 0, we'll branch to open the valve, else we'll close the valve, right? So we break it down into those basic blocks. And so usually this is an example of how we model the software control flow of the system. And it's traditionally, is anyone here familiar with control flow integrity? So it's a traditional way of just making sure that, if somebody compromises a particular basic block, right, you want to make sure that you can't branch to some bad code, which is actually part of our payload in the Harvey attack was in the physics aware attack was to create this branching condition where we branch to some bad code and drive some state estimation, right? But what we observed was that if we can break it down into this basic block level, we can actually see that these different blocks are associated with physical properties, right? So when we branch to these different states, they will actually change the flow of the system, right? Whether it's the valves open or closed, right? It will change the physical operation. So it affects this physical actuation. And so that's, in a nutshell, what we leveraged in this paper, where if you have, this industrial control system, and you have all these PLCs controlling different parts of your controller, of your ICS, and then one of these might be compromised just like before. And then you have some central control that has some historian of all the values and then other human machine interfaces, and these are all networked. Scadman would reside at the network level, and what it would do, it would maintain this, what we call, nowadays people are using the term digital twin, but it's just kind of a simulator, a replica of the system. And what we did was we took the control logic of each of these PLCs, modeled the software control flow of each of them, and then tied them to, the physical state estimation, so that we would know that when there was a variable being written to, we could change how we estimate the state of the system. And so what that looks like underneath the hood is that if we have an existing anomaly detector based on the physics of the system, and then we have some control flow representation of all the PLCs, and we take in the sensor values from the ICS network, and it updates the anomaly detector, and that's driven by this physical state estimator. And then in parallel, we are updating this software state estimator that we have, and triggering how we change the physical state estimation. And so it provides us what we call hybrid system state estimation, right? So these are just a couple of examples of some defenses that we've done in the past. And in this particular paper, we evaluated on this water treatment test bed in Singapore. And they have a lot of cool data sets, and you can actually interact with them. But they essentially had 7 days worth of operational data, and they inject attacks at different points in time. And we were able to show that we were able to detect all these attacks and with no overhead on the operation, because we're just looking at the historian data. But we have some follow-on works where, this is just an anomaly detector. And I think there's a lot of folks now are, looking at, how do you have more model the intervention component, right? So if we just detect an attack, it's one thing. It's another thing to actually, take intervention and remediate the attacker themselves. Okay. So any questions about this?
You mentioned this data from Singapore.
Yeah.
The 7 days, I would like to know if the attack occur during those 7 days or.
Yeah, so they have different types of so they have like they provide a lot of data sets. Some of them don't have attacks because they want, if you're doing like a data driven approach and you want to model the normal operation, they show, okay, this is how it looks like normally. And what's nice is that there's also a lot of cases where, you know, these systems weren't greatly engineered sometimes, and there's a lot of noisy instances where the sensor data is faulty and it causes a shutdown in the system. But then they also have attack data sets where they have 7 days worth of data, and you know they have some rough documentation, and they actually have some nice. We've had some capture the flag tournaments and stuff like that on it.
So can you go back to slide number 29?
Okay.
Yeah. Yeah, on this one. So the verifier is challenging the PLC by changing values for each input and checking whether some sensors output is changed based on the thing, right?
Mm-hmm.
So how do you guys build that input? Okay, I will test for this input and check, okay, whether.
So it was really, yeah. So in the paper, we describe how, you know, you have to know what the state of the system is. And then when you issue that challenge, whenever that might be, you have to know that, okay, maybe the robotic arm is in a particular state. And then based on its state, you can then encode, you take a measure of the software and you have to, and then encode that into the control.
So is the challenges created manually or automatically?
Yeah, so in this case, it's just like a one-off challenge, right? Like in a nonce, right? In the paper, we describe, you know, a lot of the things you have to consider even when you can issue a challenge, right? Because if, for example, obviously, if it's, you know, controlling something, safety critical, if it's in the middle of operation, you want to cause some vibrations, right? So we mentioned there's like some safety zones you have to consider when it's doing that. Yeah. So let me, let's see a better way to go through this. Okay, so we talked about some attacks, right? And now in this last, I want to make sure I'm mindful of time. So in this last section, I want to talk more about some of the meta research challenges that we have and how we even enable some of this research, because we have now some new projects that I think will make this type of research more accessible. And so I mentioned this particular test bed, from Singapore, right? And there's plenty of test beds that they have and other people have in, you know, specific isolated locations. INL has a bunch, and you know, they're really nice, right? And but there are a lot of issues, right? So sometimes, you know, it requires a lot of investment to build these. Like you have to have real systems integrators come in and build these systems, and even operate them, right? So the Singapore, in this Singapore test bed, if you want to, you know, create certain scenarios, you have to actually pay for operators to come in and then run the system, right? And it's very, very expensive. It's also inflexible. So this particular test bed, right, was built, I think, in 2012. So a lot of the technology is kind of frozen in time, but there's still a lot of research that's baked into it. And it also, you know, it's one particular type of water treatment test bed, but you know, if you look at the water treatment facilities from, you know, just across town here, you're going to see how different and diverse they are. And whether it's wastewater or drinking water, things like that. And then, yeah, more often than not, right, I think even accessing these existing test beds is challenging. I think there's so much investment that goes into it. I mean, I don't know if anyone's tried collaborating with INL, but that can be a headache in and of itself, even though they're across town. And even with Singapore, right, it really is a headache. And, you know, if you want access, you know, to the code or, you know, they're very cautious, right? Rightfully so, right? If you come in saying, hey, can I hack your system? And, you know, can I break your, you know, $10,000 PLC? They're going to be reluctant to do that, right? And so we, you know, sometimes try to build our own infrastructure. And, you know, I've been working on some research that's kind of a meta research problem about even that how we do this high fidelity experimentation. So if we have, for example, this same water treatment plant, right? We have built some smaller test beds. So this was when my first semester as part of my course, I created a very small version of this. I was using soup containers. I called it ICS to go. It was using soup containers and, you know, fish tanks, things like that, and Raspberry Pis mostly. It cost maybe a couple $100, but it was, and this is an example. I think eventually you'll see one of the students implemented an attack that poisoned the water, things like that. But it was, you know, it was very engaging, and it's even though it looks kind of silly and simple, it's. So you can see the poisoning happening here. So even though it's silly and kind of simple, it still is built on real industrial protocols, sensors, and actuators. And you know, these are protocols that you'll see in the industry, and all the attacks are actually modeled using real attacking tools and existing infrastructure, right? And we have a more mature version of this that's also remotely accessible. That's you know. We're actually having our capture the flag on this one is going to happen next week. But you know, this was one example of how we try to enable this type of engaged researchers. But even this tiny test bed takes a lot of time in maintaining it. And so we have this, you know, existing. It just started this past month. This NSF research infrastructure project where we're trying to provide these capabilities for environments for reproducible experimentation and flexibility. So it's this large, it's across a bunch of the universities. This is a huge team at Northeastern and USC. And the goal is really to provide these, you know, these representative use cases and research infrastructure that gives you heterogeneous resources. And we have the particular testbed infrastructure is kind of mature. It's been developed over you know, decades, but now we want to apply it to different types of domains. So this is the high level architecture of the overall research infrastructure, where you have users that can remotely access and do security experimentation. You know, whether it's researchers, students, things like that. And we have different domain-specific use cases. So IoT was the one developed in the first year. My component's going to be this small little box here that's called embedded CPS nodes. But it's small in this picture, but it's actually going to be the biggest one. And what we are proposing so we just worked with the systems integrators to, you know, to formalize this, right? And the idea is that we can provide you access to this, you know, an actual real industrial control system. We're working with Rockwell Automation to build this big research infrastructure. And instead of, you know, just asking somebody to do these experiments for you, the goal is to provide virtual access to all the components of the system. And, you know, with HMI or the programming operator, the SCADA system, things like that. So this is a project that we just started building, and the goal is to have, you know, eventually we're coming up with ways where you can have it just interact with different types of control systems. So we use common industrial control system infrastructure, and then you could essentially model a large water plant, or it could be a smaller water plant here, or it could be an oil treatment plant, right? But all these usually have a common infrastructure. And so this is it just started this year. We have the initial use cases will be water treatment, and and some other local utilities. We're working with the Los Angeles systems integrators who build all these systems for mining operations, for even SoFi Stadium, things like that. And they're providing us with kind of real use cases that, or at least models based on real use cases, to provide what we call these digital twins. And there's a lot of research challenges here in terms of just how we model the fidelity of the experimentation itself. So this is one project we're excited about. We envision maybe like in a year, we'll start beta testing it. But if you're interested in this type of research, or at least getting engaged with it, we'll have at least certain components up and running, you know, in a few months. Yeah. So again, there's a lot of ways you can engage with this, either as researchers or, you know, we envision local municipalities or, you know, engaging with government PMs, things like that. We presented this even to local utilities. So I presented this to a water treatment conference, and we have folks who are interested in, you know, the operators of the real systems engaging with this, and maybe even using this as security training exercises and all that. Okay, so I mean, in the final concluding thoughts, it's mostly just talking about some other maybe one-off projects that. So we have this. I just want to mention this other project, and I guess you can think of this as a bioengineered system. So this is more on leveraging sensor data to decode how humans encode memories. So we're working with patients with real implants, and working with it. So it's at the intersection of AI for sensor data and making sure that, you know, if we're developing interventional policies for different types of memory retention and stimulating the brain in particular ways, we do this in a trustworthy way. So this is one-off project that we didn't really talk about. And then another project that we're working on is, again, if we have a similar structure like we did before. So this is more on the formal method side of things. And we have the same PLC here. We are actively working on projects where, you know, if we have some safety requirements, we can have ways of modeling these PLCs in a more formal way and verifying based on the physical dynamics, whether it's going to violate any safety property. And we have this bidirectional translation where we can use interactive theorem proving tools to verify that this program is safe, and then translate them in a syntactically and semantically correct way to code that's going to actually run on these PLCs. So this is a more, I guess, a more theoretic project, but there's a lot of challenges even here, and how these, and we're also including ways in which these interact with their digital twins, things like that, and how, you know, if you're monitoring these systems. So there's a lot of one-off projects from this NSF project. And so to conclude, you know, we showed a lot of different attacks where attackers leverage the physical properties of the system, and we showed ways that we want to retrofit security. And we're actively building these large test beds with real-world use cases that I'm hoping to engage with the community and get more people access to ICS security research. And then there's a few other ongoing future work projects, but I'd be happy to take questions about any of this. Yeah.
Thank you so much. So I think we all enjoyed your presentation, and you have been doing very great things, and even working with the famous Singapore water plant. Yeah, so these things are amazing. So I know that the test bed, the real test bed that you have been working on, they are never equivalent with the virtual ones. But since the real ones are expensive and difficult to maintain and difficult to access them, so is there any equivalent the virtual test bed or something that can facilitate your research or related research?
Yeah, and so that's a great question. So there's now, so even the Singapore group also started coming up with this, they call it reconfigurable digital twins. And we're also we want to adopt, we're integrating that into ours as well, where we're looking at so in their case, they're looking at digital twins as, just simulators. And so in theory, you can use these high fidelity simulators. For the most part, they work well, but I guess the fidelity of that, so how well they're modeling, is a meta research problem that is something we're exploring. In our case, with our big test bed, we're actually, the goal is to have these reconfigurable nodes. So we're thinking about ways where the PLCs will actually be signal generators for other PLCs. So if you want to run one type of experiment, you're going to be able to generate those signals in a way that the system won't know it's interacting with a simulator. So that's our goal with that test bed. And we're also thinking about ways where, so we interviewed a lot of folks in the community. And I think right now, if you look at a lot of the research, because they're so expensive, people will buy, their own PLC or their own Raspberry Pi, and you don't know how real it is, right? So what's the impact of my, whatever research I'm doing on this PLC? So we want to provide some bring your own device abstraction so that you could be hacking your PLC locally, and then you could see it in the operation with the rest of our system. So we'll provide some, VPN tunnel that will allow you to connect. We'll provide some abstractions that allow you to connect your system, and then you could, hack it accordingly. So that's a goal of what we're doing. We're actively, we're designing it right now, and just it should be up and running hopefully within it. That's a goal at least. Yeah.
So just, I'm thinking about SCADMan and anomaly detection in general. What is the risk of a false positive in this type of a setting,
Yeah.
right? Like, if we can't, like, what if it says that's an anomaly, but there's not? Like, what's the risk there?
Yeah, so it's a good question, right? I think for the most part there's definitely a usability issue. I think people are going to complain, especially the folks that are reluctant to adopt these types of solutions. And so, I mean, for the most part, if you have a false positive, for what we were doing, it would just raise a flag and say, hey, something's wrong. In that particular SCADMan approach, there's some limitations where, it wouldn't be able to discern between an attack versus just faulty sensor data. The counter argument is, if you do have faulty sensor data, what we found was that the faulty sensor data itself would cause change in the actuation. So if, the level goes up to 1,000, it's going to shut down the system. And those are, even though they're false positives, it's still, false, right? You detect the faulty engineering itself. But we do have, follow-on works where we're looking at including more of the system provenance level analysis. So looking at, how you can figure out what's happening at the network and operational level, and then using the system logs kind of, reduce a lot of those false positives and figure out, not only reduce the false positives, but figure out what happened in the system level. Rather than just treating it as, okay, there's a discrepancy in our digital twin versus what's happening in the black box.
Thank you.
Yep.
So, the project you're showing, like formal verification to go
Yeah.
to and vice versa. Is it an ongoing project, or are you guys
Yeah.
planning to do it?
So we have a paper on this, but then also we're scaling it up more now and including digital twins. So I've been mentioning digital twins a bit, and you can think of it as just like a simulator of the system. And we spoke with the systems integrators to see, what's kind of out there, at least in Los Angeles. And it is an emerging technology where, people are using them to kind of project what's happening in the system, but municipalities are really reluctant to use them. And there were some interesting cases where, they're saying maybe there's some municipalities where, like, in their cases, what they want to do is create a digital twin and then try to project what's happening. So in LA, they're particularly interested in this because the Olympics are going to be in 3 or 4 years, and they're pretty much telling operators, hey, like, you know, your system works okay now, but you see a lot of failures, and are you going to be able to handle double the population in your city, like wastewater, water treatment, power grid, all that, right? So you want to create a system not only to monitor, but also to project what's going to happen. So this is, in only a few places have adopted this, and you see a lot of issues. I mean, right now, like the sewage waste treatment in Los Angeles. Has anyone been to Los Angeles? There's a lot of issues sometimes where if something goes wrong in the wastewater treatment, they just dump it into the ocean. That's kind of like the current model right now, and they say don't go swimming for a couple weeks. You know, it's not really a good model, and that happens now. Imagine when you have all these people coming in for the Olympics. Yeah.
So for this, I guess you guys are using some kind of pre-trained model and fine-tuning them with a specific set of data set, right?
Yeah, I mean, this particular project assumes that you have correct physical representation. So you have a set of physical dynamics for it. That is a whole other challenge in and of itself, right? So yeah, there are ways to monitor how good your model is. That's part of it, right? And that's why I mentioned digital twin modeling is what we're looking at, right? Is, you know, how well can you estimate the system, because it's pretty critical to a lot of these industrial control systems. And the good thing is that, you know, we can build these physical representation because these systems are meant to continuously run the same operations, right? It's industrial automation. We have a lot of data of what's happening. It's a lot of repetitive things that happen. Yeah.
In the SCADMAN where you're using control flow graphs to represent, so I just want to understand it better. Is it representing the expected and the observed values of sensors and creating a control flow graphs of it? And if there's any like anything out of the ordinary, then it will take it as a map or something?
Yeah, so it's both. Let me see. I think here. So it's both the building, yes, a state estimator so the state estimation is really just some physical modeling software that just monitors the sensor values, right? And then we're building a control flow graph of the software that's running on these devices. So I think we have it here, right? So the control flow graphs are the logic that's running on these devices. And in the paper, we talk about how we consolidate a representation of them to monitor what the software operation should be based on the sensor value. So it's a little bit of both, right? So you're coding the sensor dynamics into the control flow modeling of the software. If that makes sense.